Good afternoon, everybody. Welcome back to the Journal Club. Today, it is my pleasure to introduce to you Rodrigo Calderón. He's a postdoc student at the Institute of Physics in Prague. And today, he will be telling us more about assessing the viability of early dark energy in light of the new data by ACT and DESI. So please, Rodrigo, feel free to start whenever you're ready.
Yeah, thanks a lot. Thanks for the invitation, and very happy to be able to talk about this work. So this is based on this preprint that we put out last month. So this was done in collaboration with Vivian Poulin, Tristan Smith, and Theo Simon. So of course, all these things, Vivian and Theo in particular, have been working on early dark energy for years. And I'm just gonna update some of the constraints and what we have learned since the arrival of ACT and DESI. So before I start with the early dark energy, I wanted to kind of briefly remind people what we all learned in middle school when we were taking the first cosmology or astronomy lectures. We learned about these things called standard candles. So these are objects with known luminosity in the sky. And so if we have an object with a known luminosity in the sky, we can infer its distance by measuring the flux. So this is similar to what our eyes does when we look at the headlights of cars coming towards us. Our brain is able to gauge the distance at which the car is from us by estimating the luminosity of the car, of the light sources. And this is done because we know that cars have an intrinsic luminosity, so our brain is able to infer distances from this. Another type of object that we can use to infer distances are what we call standard ruler. So this, for instance, these are objects that have a known physical size in the sky. So if we know their physical size and we measure their angular size in the sky, then we can infer the distance to the object by doing simple trigonometry. And so standard candles are useful because there are things called type 1a supernova that can be standardizable, and we can measure the apparent magnitude MB as a function of redshift. Depends on the cosmology through the luminosity distance, but it also depends on the absolute scale of the supernova. And so by measuring this MB, we can extract the cosmology which is encoded in the luminosity distance. And so in this sense, we can only measure relative distances, relative to the absolute magnitude for the case of supernova, and relative to the size of the sound horizon at the Dirac epoch for the case of baryon acoustic oscillations. So this is important because we only have measures of relative distances, and importantly, these two distances are not equal. So this was a surprise to me. What I was learning in cosmology is to realize that there are various notions of distance. But what is crucial is that even though they are not equal, they probe the same expansion history. So just to remind you, distances are often proportional to the integral of the Hubble rate, the inverse of the Hubble rate, or directly proportional to 1/h. And so interestingly, if you have some reasonable assumptions, you can relate how the luminosity distance is related to the angular diameter distance. And so for metric theories of gravity and under the assumption of photon conservation and so on, we can derive this relationship, which is valid for any cosmological model that respects these assumptions. Of course, you can relax these assumptions, and I invite people to have a look at this paper if you're interested. But what is crucial is that we can, if we have measurements of luminosity distance and angular distance, we can put them on the same footing by converting one of them to the other, assuming this distance duality relation holds. So this brings me to what we call the cosmic calibration tension. Because if you do this game and you play this game of converting the BAO measurements into luminosity distance measurements, you get these type of diagrams. So here I'm showing the red data points are BAO measurements, and the blue data points are supernova measurements. So here you see that the supernova measurements, in fact, it's order 1,500, but I've binned them into 30 bins so that you can visually see what's going on. But just know that the full analysis is done with the full data set. And so what you can clearly see from this plot is that the DESI or any BAO measurement that is calibrated with the value of the sound horizon you infer from the CMB, that would give you points that are scattered around this red line. And now, if you take the supernova measurements and calibrate them with the value of MB that we measure with Cepheids or any other low redshift local calibrator, then we get these blue points. And you clearly see that these two are very separated. And if you wanted to bring these measurements into agreement, you would have to imagine having cosmological models that kind of oscillates back and forth and fit both Hubble diagrams as probed by BAO and supernova. However, as I said, this is only possible because we assumed the distance duality relation holds, and we assumed that the BAO are calibrated with the CMB. However, as I said, we don't really measure RD. We can only measure the ratio of the angular diameter distance with RD. And so we are free in some sense to change this calibrator. And so for now, I'm not talking how do we change this calibrator, but you can clearly see that if you change the value of RD, now I'm decreasing the value of the sound horizon, and all my BAO measurements are basically coming down and are very much consistent with the Hubble diagram as probed by supernova. And so from these kind of plots, it is clear that the tension is more than just H naught. It's something that has to change the calibrator of the uncalibrated distance measurements that we have from supernova and BAO. And this is what the early dark energy model does. So again, there are other early type solutions that lead to this same decrease in RS, but overall, the whole point of solving this tension is bringing the BAO measurements in line with the supernova ones. So before I move on and discuss constraints on the early dark energy, I would just to briefly say what the main take-home messages are. So if people want to disconnect, they can disconnect from now on. But I think that these are simple and important messages that we need to necessarily understand better what's going on in particular in terms of the data. So the first take-home message is that despite the increased precision, the new measurements by ACT and DESI in fact favor a significantly larger fractional contribution of the early dark energy. So I will often refer to this FEDE, which is just a fraction of early dark energy with respect to the total energy density at this redshift ZC. So if you take previous NPIPE and SDSS data, basically the constraints were very strong, and I will show those. But it's counterintuitive to have better measurements and to have less constraining power. So that's the first take. And the second take that I would like to emphasize is that Bayesian analysis, in particular, those that do not include shoes, are in fact subject to prior volume effects. And this is something that has been studied before and it's known in the literature. But I still think that it's important to emphasize that some of these analyses are subject to these effects and we should be careful. So these are the constraints that we had on early dark energy before ACT and DESI. So here I'm showing the constraints you get from Plick in the dashed lines compared to the ones you would get if you were to use NPIPE. So for those of you who are not experts on this, NPIPE is just a reanalysis of the PR3 data with a slightly higher sky fraction and different way of cleaning the maps if you want. So the NPIPE is the new version, and you see that going from PLIC in dash to NPIPE, the constraints on this fraction of early dark energy are quite stringent. So we are not consistent anymore with the shoes measurement. We are more than 3 sigma away. And it seems that if you have this NPIPE data, early dark energy looks like not a promising solution to Hubble tension. And you can also look at frequentist likelihood profiles. So this is where you look at how the chi-square changes as you vary one parameter, in this case H naught, and you marginalize over all the other directions. So you obtain this kind of profiles, and from this profile you can compute the 1 and 2 sigma regions by looking at how the delta chi-square changes. And so you see that again, the frequentist analysis gives consistent results with the Bayesian analysis, and it doesn't favor EDE as a solution to the Hubble tension. You see that PLIC is still a bit more permissive, but there is not a huge difference. And now if I go to NPIPE versus what PACT tells us, so now NPIPE is in the dashed lines. You see we have this stringent bound on FDE, EDE. But now you see that as you go from NPIPE to PACT, you see that there is a shift in the posterior distribution of H naught. So the constraints so the posterior of H naught not only shifts, but the constraints are in fact weakened by a factor of 40%, which, as I said before, it's very counterintuitive because we expect that better data will give better constraints. And in fact, if you compare in ΛCDM, the PACT constraints are as good as NPIPE, and they are 20% tighter than PR3. But in early dark energy, as you see, the constraints are weaker, and there is a shift towards higher H naught, which I find it quite interesting. And this is reflecting somewhat the preference for ACT for more power at high multiples. So in DR4, we used to refer to this as a preference for NS going to 1 or consistent with 1. Now this preference is less, but it still prefers higher power at higher multiples. So this is what I think it's driving this shift in H naught and FED. And now if we look at what DESI brings into the discussion, you see that we go from Planck, ACT, and lensing and supernovae to the solid ones, which again are shifted towards higher H naught values, and they allow larger fractional energy densities, early dark energy contributions. So to understand why DESI pushes even further to higher H naught, I think it's quite interesting to see in this plane. So this is taken from the DESI paper, DR2 paper. So this assumes ΛCDM, and you see here that we are starting already to see the problem. So DESI favors a higher H naught RD with respect to what the CMB prefers. And it also favors a lower omega matter with respect to what the CMB prefers. And so early dark energy, by increasing the value of H naught and decreasing the value of RS, in fact, is pushing you from the blue towards the red or black, if you want. So by allowing for a non-zero FED, you are in fact moving in this direction, which is what the CMB wants if you want to be in agreement with what DESI wants. And this omega m H naught RT tension, if you want, is also somewhat responsible for signs of dynamical dark energy and so on. There is another discussion in this DESI paper where they looked at these kind of things. And yeah, to basically the money plot that I wanted to show is this, which I think makes this, the situation very clear. you can see that the dashed measurements corresponds to NPIPE and SDSS, so before ACT and DESI. And you see that they all favor values of H0, which are around 68, unless you give a Schuss prior. But now with the new data, you see that the H0 values that the Bayesian analysis wants are higher. But in particular, the frequentist is very much different between the two and is very consistent with what Schuss measures. So I think that one of the interesting things about this plot is precisely the blue one, where you see that having a frequentist analysis can give you different results than the Bayesian one. And as I said, these things have been studied in the past. Many people in this community have worked on this frequentist versus Bayesian constraints. And so we know already that these models, this type of models, suffer from what we call prior volume effects. So this is when, for instance, the fraction of early dark energy goes to 0. There is essentially no difference in chi-squared values because the model is indistinguishable from ΛCDM. And this leads to a large number of possible parameter combinations that have a similar chi-squared, and it gives more volume effects that when you marginalize, it can lead to projection effects and so on. And so the answer to which one of these two to trust is, I would say, none. We should do both, and we should compare both. And having consistent results would just tells us that the measurements are good enough and that our posteriors are Gaussian enough. And for the time being, this is not the case in early dark energy. So we should wait for better data, or see what the future lies. So if I finish by looking at the likelihood profiles, again, comparing previous data with the newest data, you see that as we move from NPIPE to PLIC, you do move towards higher values. And if you use the newest version of the data, then you get something which is much higher than the previous data releases in H0. And a similar trend is visible in the fractional early dark energy. So you see that in the case of p-ACT, lensing, BAO, and supernova, we are actually detecting at 2 sigma non-zero contribution of EDE. So I don't know how I'm doing with time, but maybe I can start summarizing. As I said before, I think that it's quite interesting to see that new data actually favors larger FED contribution. This was kind of unexpected. I think Vivian or anyone expected this. So the tension with Schuss has gone down from 3.7 sigma to 2 sigma. And this is somewhat traced back to the fact that EDE improves the consistency between DESI, in particular the low matter densities and higher H0 or D values. And even though it improves the consistency between DESI and CMB, there is still somewhat of a tension between the matter densities that we infer in the early dark energy model and the values favored by the supernovae data. So this is something that probably is telling us that even though it might help, it's not fully resolving this dynamical dark energy claim in the literature. And so, yeah, as I said, I think that this is a perfect exercise that shows that Bayesian analysis should in fact be complemented always by frequentist approaches, in particular when we are dealing with these extended models where we have regions in parameter space that lead to very similar predictions for the observables as ΛCDM, so you can artificially disfavor these extended parameter spaces. And yeah, I guess that this is something interesting because if it's the case for ED that the constraints got weaker, it might be also the case for other models in the literature. It might be worth revisiting some of the models that we thought were ruled out. And yeah, these are more speculative thoughts, but I think that if we indeed are seeing that measurements are showing hints for a breakdown of ΛCDM, whether you take it to be dynamical dark energy or these phenomenological negative neutrino masses or non-standard dark matter evolution, it is clear by now that something is going on. And I think that one of the things that we should be very carefully investigating is the different CMB likelihoods, in particular, because these are often related to new physics. So we have the A-lens anomaly in Plick, for instance, and it might be that if there is indeed new physics, these anomalies that we were seeing are not in fact anomalies. It might just be reflecting some beyond ΛCDM. So I think that the times are exciting and looking forward to the data. Thank you very much.